All right, let's start. Welcome to this talk on the properties of LDGM-LDPC codes with application to secrecy coding. I'll just give you a brief outline of my talk. The first part of the talk is an introduction to LDPC, LDGM codes. We'll talk about regular and irregular LDGM and LDPC codes. In the second part of the talk, we'll investigate some code properties like the decoding complexity of irregular LDGM and LDPC codes over the binary input symmetric output memoryless, or what is known as the BISOM channel. We will show some lower bounds on the complexity of these codes. Essentially, what we will do is we will construct a model code of the irregular LDGM and LDPC codes, and we will puncture some bits of the model code. Okay. This model code is actually a punctured LDPC code, which enables us to use the upper bound, which was derived by LDGM, the upper bound of the rate. After that, we look at some stability conditions for iterative decoding of the model code over the binary-erasure channel. And part C, which is the third part, is we'll apply these codes to secrecy. Essentially, what we do is we exploit the fact that regular LDGM and LDPC codes achieve the capacity of the binary-symmetric channel with finite degrees, and we will use that fact to in fact construct a secrecy capacity achieving nested code construction for the type 2 binary symmetric architecture. So that's about it. So let's look at what an irregular LDGM LDPC code is. And it is in fact a concatenated code. It consists of an LDPC layer, which is in some sense a precoder, and then the pre-coded code words act as the information symbols for a low-density generator matrix layer. Okay. The key idea here is that both the LDPC and the LDGM matrices, the matrices which define them, which is the parity-check matrix here and the generator matrix here, are sparse. So that's the idea. G is the generator matrix of the LDGM code. H is the parity-check matrix of the LDPC code. We'll come to this picture later. We keep coming back to this picture. The code word is essentially defined as x1. The x1 is a random vector. x1 is x2 times g, where x2 is in fact the sequence, the LDPC coded sequence. Okay, so this is an irregular LDGM LDPC code. Of course, if you look at the same code we saw in the previous slide, and if you regularize it, which means that the lower code is a DC prime regular code, and the upper code is the accumulate nodes of the upper code are regular, then you have a regular LDGM LDPC compound construction.
You might want to say what lambdas are and all this. You just keep that in mind.
Sure. I'm sorry, I forgot to mention that. So the essential idea is that when you look at the factor graph representation of these codes, the distribution of edges is controlled by some probability function. And essentially, lambda is the generating function for the degree distribution from the edge point of view. And similarly, you have degree distributions from the upper matrix.
So why do you describe a system by the lambdas and not just by the h and the g? Why don't you just say, a code given by h and g? Like you sort of think to be like a code given by lambda h and lambda g. And
sure.
Is that just a convention, or is there, that you borrow from others? But if it is, then why do they do it that way?
So when we talk about a sparse matrix, whether it is a sparse generating matrix or a sparse parity-check matrix, the convention is that you pull these matrices randomly from some ensemble. And how you define them, for example, for the LDPC code, how you define them is you start with some generating function for the edges, lambda and rho. And essentially what you do is that then you have a permutation defined on the edge. Sure. So how do you generate the ensemble? Is that you pull an element out of you pull an element with the edge degree distribution defined by these distribution functions, and then you have a permutation which is uniformly chosen. And then as you choose a different permutation, you get a different code. So from one distribution, as you change the permutation, you get different parity-check matrices.
Okay, so you're using the lambda to refer to the ensemble of code which has matrices with these distribution properties.
Because for many properties of the code, what's important is the lambda and rho, and you can generate a randomly code and it will satisfy these conditions as long as lambda and rho have certain form.
The essential idea is that as you obtain these codes, there is some very strong concentration results. So let's look at what a code word for a regular LDGM-LDPC code is defined as. So essentially the code word is an n-length binary sequence such that x of n is equal to g of ym. Ym, as we saw, was the output of the LDPC codes. And ym, in fact, satisfies the parity-check matrix. Let's look at some nested properties of regular LDGM and LDPC codes. In fact, we'll be using these nested properties for secrecy coding. How do we achieve nesting? Is as follows. Now this is the lower LDPC constraint set, or the parity checks, and we divide the parity checks into two classes, H1 and H2. So the lower H matrix is partitioned into H1 and H2, and to in fact obtain nesting, let's look at what the fine code is. The fine code consists of all the n-length sequences, which are the output, such that the pre-coded inputs satisfy the first set of constraints. So what you do is you look at all the code words which satisfy only the first set of constraints. So that's the fine code. It's called fine code simply because there are more code words in it. And then you look for the coarse code, which is contained in the fine code. And how do you do that? You start changing the value of the parity checks for the second set of constraints. Okay, and as you change the value of the parity check, you in fact get disjoint. What do you call this? Disjoint coarse codes, such that they partition the original fine code. So that's what you do. As you change R, you get different coarse code, and all these coarse codes put together consist of fine code. So this is how you get nested LDGM and LDPC. So the second part of the talk consists of the decoding complexity of the irregular LDGM and LDPC codes. And as we all know, there are two fundamental problems in channel coding. The first is, of course, that if given a channel, you have to construct codes which come very close, whose rates come very close to capacity. And then the second question is, given that you have these near capacity codes, how do you decode them initially? Now we have Alexander Vardy's famous result that for the binary symmetric channel, the ML decision problem is in fact NP complete. So you need some other way of decoding these codes initially. And let's suppose that we have a code ensemble which achieves a rate 1 minus epsilon times c, where epsilon is some quantity between 0 and 1. Okay, and c is the channel capacity. Kallikar and McAleese, in fact, conjectured that the encoding and decoding complexity of the code will in fact be proportional to log of 1 by epsilon and 1 by epsilon times log of 1 by epsilon. This was conjectured in the year 2000, and this was for MPI decoding. Let's look at some results for the LDPC code ensemble. And actually, this result is more general. It's for any class of parity-check codes. And we define the density as the number of ones in the parity-check matrix per information bit. So why is the density important? It essentially puts an upper bound on the number of messages which are exchanged in one round of iterative decoding. And Irregular in 2003 showed this lower bound as K1 plus K2 times log of 1 by epsilon. But K1 and K2 are some parameters which do not depend on the code, they depend only on the channel. And this result was for a full rank parity-check matrix. And essentially, if you see what happens in the limit epsilon tends to 0, which means in the limit that the rate achieves, the rate moves very close to capacity, is that the lower bound on the density becomes unbounded. So this was a strongly negative result. Basically, it shows that using the very successful LDPC coding paradigm, you can in fact never get very, very close to capacity without an explosion in the lower bound of the complexity. So at that time, the question was asked, and suppose we have more sophisticated or complicated graphical models, can you in fact get rates very near capacity with finite graphical complexity? And essentially, the first move in that direction was by Henry Pfister and Irregular in 2005. But what they did was they took a non-systematic irregular repeat accumulate code. Here it is. This is the factor graph of a non-systematic irregular repeat accumulate code. So what you do is you have these information symbols or information bits, and the first thing you do is you repeat them. So let's repeat. Then you have permutation, and then you accumulate the bits. So this is a non-systematic irregular repeat accumulate code. What Irregular, and Pfister showed was that if you punctured the information bits with a probability which was 1 minus order of epsilon, in a sense, you could get rates very close to capacity with a finite complexity. And they in fact showed some degree distributions for that. And that work essentially inspired some other work. Basically, people started looking at getting higher rates with puncturing. And there was a work by Hu in 2008 where they look at randomly punctured JK regular LDPC codes. They use an ML decoder for a BISOM channel. And Irregular has another work where he essentially looks at parallel LDPC codes where now the variable nodes are partitioned into j parallel channels. And in fact, he shows that once again, if you choose the functioning probability very carefully, you can essentially have a lower bound on the complexity, which is finite.
But is a lower bound on complexity what you want? I mean, doesn't that just say, oh...
So all these results are essentially existential. They are saying that, well, strictly speaking, you would require an upper bound on complexity.
Yeah.
And then you would say, look, I punctured, and then the upper bound becomes finite. But as
wait. So is it an upper bound or on decoding complexity or a lower bound?
this is a lower bound.
So finding a lower bound says, oh, you can't, no matter what you do, get decoding complexity better than that, or be less than that.
Yes.
So it's a negative result.
Well, if the decoding complexity, if the lower bound is unbounded, then it's a negative result. If it's finite, it just means that it may be possible.
So is this a positive result or a negative result?
It's not a negative result.
I mean, I guess isn't that thing blowing up as epsilon goes to 0?
No, it does not, because as epsilon goes to 0, there is a way you can choose this function probability such that this function is in fact finite.
K2 is the function because
If you use a
puncturing
puncturing probability, you tune in.
is kind of a trick. So I guess
So somehow-
reports on lower bound are motivated by the result of Schrodinger. The one where it blows up. So Sasson and Wickman, they said, okay, LDPC codes are not so good because the lower bound blows up. So then, instead of finding an upper bound, the easier task is to find necessary condition, sort of prove a necessary condition. Find codes with a lower bound, which doesn't blow up.
So these lower bounds have to do with essentially like the amount of communication that's going to happen with the decoding, the amount of message passing. So is the belief that this kind of characterizes the order of the complexity needed for decoding? Just that even though they're called lower bounds, people feel that
The assumption that
they have kind of the right order properties.
Yes, that's exactly what it is. In fact, some degree distributions for the NSIRA codes have been suggested, which in fact are pretty close. So if you see the state of the art, there are all these lower bound results, and for a certain range of rates, there are different ensembles. So that's all there is right now. Someone has to come and show sufficient conditions. Then there was another class of codes called the accumulate, repeat, accumulate, or ARA codes. Essentially, these are the systematic bits. And what you do is you first accumulate, and you again repeat, and then you accumulate. So this is an IRA code, and on top of it you have an accumulate structure. And essentially these codes perform very well at finite length. And this showed some capacity achieving degree distributions with finite complexity for the binary-erasure channel. There are some results for the regular LDGM-LDPC codes, which were studied by who showed that under ML decoding, if the right average degree is greater than a threshold value, you will suffer no loss in dimensionality of the code. However, for their work, they assumed an upper LDGM code which has a rate 1. So the upper LDGM layer is just acting like some kind of a concentrator. It's not tuning the rate. And they gave some capacity achieving degree distributions for regular LDGM-LDPC codes. And this was the paper which originally got me started on this whole thing. This paper by Wainwright, where they essentially look at regular LDGM-LDPC codes ensure that they achieve the capacity of the binary-symmetric channel with finite degrees. Okay. Now let's get on with our proof. So the first thing we do is we take this code, we take the factor graph of this code and fold it around. So what we're trying to do is we're trying to convert this into some sort of a punctured LDPC code so we can use existing bounds which are known. So to do that, we took the factor graph and we twisted it around so that the intermediate LDPC variable nodes which were here in the factor graph now move up there. So this whole sequence is like a LDPC output. So you define that as the code CH, where the code word is x1 concatenated with x2. So this is x1 and this is x2. X1 is a binary code word of length n1, x2 is a binary code word of length n2. And essentially you can show that this code CH has a parity-check matrix which has this form. Okay. G is the generating matrix of the LDGM layer and H is the parity-check of the LDPC layer. And the proof is kind of straightforward. You can essentially see that this is in fact the parity-check for this code. So we have some sort of a LDPC code. And now what we do is we start puncturing the bits of x2. And we take the bits of x2, these LDPC variable nodes, and we start puncturing them independently with probability p. And we call that code CH of p, which is the code CH whose LDPC variable node information bits are punctured independently with probability p. And of course we can see that in the limit p tends to 1, C of h is equal to the original LDGM-LDPC code, because essentially what you've done is you puncture all these bits. So all that is left is this, which is the code word of the original code that we started out with. This is a bound on the entropy, which comes from Sesson's 2007 paper. He talks about transmitting an LDPC code over J parallel channels. So his result essentially is that partition the variable nodes of a LDPC code, and each one of these travel on a separate BISOM channel. So this is BISOM channel 1, this is another channel, and so on. What is the performance of these codes? So they give this lower bound on entropy. And essentially what we do is we just consider the case j equals 2. So we are interested in the case j equals 2. And why j equals 2 we'll come to in a short time. So first let's see some of the things here. RD is the design rate of the parallel LDPC code. C of j, this is C of j is the capacity of the jth parallel channel. GJI is a function of the LLR on channel j. We define this later. P1 is the fraction of nodes, is the fraction of bits which travel over the first parallel channel. P2 is the fraction of bits which travel over the second parallel channel. And so this is the bound on the entropy of x given y. So first let's look at the channel model for CHP. What we do is you have the bits x1 and the bits x2. Just to remind you what CHP is. So this is the code CH. We saw this before. And then you start puncturing these bits independently, you get CHP. So we model that like this. We take the bits x1 and transmit them the way they are over a BISOM channel with capacity C. We take the bits x2 and we puncture them independently with probability p. In fact, the capacity of this BISOM channel becomes 1 minus p times c. That's because that's asymptotic in limit of n2 going to infinity. That's the average number of unpunctured bits. And in fact, the output of this channel is y1, and the output there is y2. And essentially, the capacity of this channel is n1 times c. The capacity of that channel is n2 times c, 1 minus p. And this is a lemma which we prove for the upper bound on the entropy of x given y for the code CHP. You can see this follows from Fanner's inequality. Now we use the bound in lemma 2 in the result of proposition 1. We set the probability of error to 0. And by the way, proposition 1 is for a given code, which means that the betas are random variables. So we compute the expectation over betas, and we get this upper bound on the achievable rate. So this is the highest rate which the code CHFP can achieve. We know what P1 is, we know what P is, we know what C is, and the only thing we don't know is RH, which is the rate of the lower LDPC. And now what we do is we say, okay, we have this code CHFP, and let's suppose that the design rate of CHFP is within an epsilon multiplicative fraction of the capacity of the original channel. And in fact, if we set that to be the rate, we get this lower bound on complexity. And once again, you see there's trouble because the denominator of this term is proportional to epsilon. So when epsilon in fact tends to 0, the numerator becomes unbounded. So what do? We look at G21, and what we see is G21 is 1 minus P times G1, and again we invoke.
Well, it's defined in this.
Right. So G21 would be, in fact, this is the log likelihood on the second channel times this function. This function actually it measures in some way how noisy the channel is.
ELT is actually a little bit of a conditional log likelihood here, right?
So strictly speaking, AL of 2 would be the log likelihood ratio on the second channel, given that the all zero code word was transmitted.
So it's hard to get a sense of what.
Well, let's put it this way. If the channel is very noisy, if the reliability of the channel is near 0, then GJP would be close to 1. And if you have a channel which is almost noiseless, GJP would in fact be close to 0.
Okay.
So that's all you can do. That's the only way you can do it. So in fact, when you observe that G21 is 1 minus P times G1, we use the familiar trick of puncturing at a certain rate. The essential idea is that then the right-hand side becomes finite. Okay. So the question is, can the lower bound be finite when epsilon in fact tends to 0? And the answer is a yes, and that is lemma 4. Essentially what we do is we say that the lower bound on complexity of the LDGM-LDPC code is finite over a BISOM channel. So what do? Well, we say if epsilon tends to 0, when epsilon tends to 0, we puncture with a rate which is 1 minus k times epsilon, where k is a constant, which depends on G1.
Somehow what's missing in this is, the previous slide, gives a complicated expression in terms of average left degree, average right degree, and then the rate of the LDPC code and the number of assigned bits, right? And how to relate that to the what you call complexity, which is the density of the two codes, right?
Well, the problem is that for this code, you can't really have separate expressions for A of L and A of R. A of L and A of R are the average left and right degrees. So here you cannot get a clean expression for them separately. The best you can do is you can say that the sum of these two.
So it's a weighted sum of A.
It's a weighted sum of both these is greater than or equal to some quantity which by smart puncturing can be made finite. Okay. Now it's very interesting to see the effect of noise on this weighted sum. You can look at that. Like when G11 changes, why is it that AL carries more weight than AR? You know.
So if the weighted sum of AL and AR, if it blows up, then we're in trouble.
Sure, and that's one thing, but also if the lower bound is finite, then both of them are finite.
Not necessarily.
So why not?
Why are they finite? It's just the lower bound.
Oh, sure.
That's your continuum. It's a
Sure, I
necessary,
agree. Sure.
it's a necessary condition.
We should say, strictly speaking, it's an existential condition stating that yes, it may be possible that you have good code sequences.
But it's not an existence, you know.
It's a necessary condition. And in fact, later in this talk, I'll sort of talk about why we don't have upper bounds and what we need to look at to get upper bounds. So what do? We set epsilon going to 0, and we see that the lower bound on complexity of CHFP is finite if we puncture in a certain way. And by the way, as epsilon tends to 0, the puncturing probability goes to 1, which means you're puncturing almost all the bits of x2. And by claim 1, we've seen that when you puncture at rates very close to 1, CHFP becomes equivalent to the original LDGM-LDPC code. And by this time, like, there are lots of questions about lower bounds and complexity. Like, why are we talking about lower bounds when we should actually have an upper bound? So the point is, what we have is essentially a lower bound in complexity. And all we show is that the lower bound does not blow up, okay, as epsilon tends to 0. What can be done is we can derive degree distributions over the binary-erasure channel. If we could derive degree distributions for the binary-erasure channel, which achieve rates very close to capacity with finite complexity, then that is proof that in fact those sequences are possible. But to get there, we need density evolution equations. That's the standard technique to derive degree distributions. So that's what we'll do next. What can also be looked at is the lower bound type. So once we get these degree distributions, we can essentially see if the bounds that we had are tight or not. And this is, by the way, just some intuition as to what we need to do to get the desired upper bounds. What's not clear is this. Suppose you have an ensemble of parallel LDPC codes. How do they perform under puncturing? Under what conditions do you suffer a dimensionality loss? So essentially, the idea is this. The rate of a code is k by n. K is the dimensionality, and n is the length of the code. To increase your rate, you would ideally want to have puncturing, as Professor was saying yesterday. You would like to have a puncturing scheme which reduces n. Okay, so the idea is that you start chewing up a few variable nodes here and a few variable nodes there, such that you can reduce n without sacrificing k. But eventually what will happen is that you will land up screwing the dimensionality of the code. You will puncture far too aggressively, and in fact, you will end up hitting the minimum distance of the code. And then, essentially what will happen is that you will start suffering serious dimensionality loss. Okay? So it's my intuition that the reason that there is no upper bound in any of the literature, either for NSIRA codes or any of these codes which do this magical trick with puncturing, is that we have not looked at how we can puncture a parallel LDPC code without dimensionality loss. To truly understand that, we would need to have some idea of the spectrum of that code. And then we could discuss how we can puncture each one of the J subchannels. That's in fact a very interesting problem which can be looked at. Okay. So now let's look at density evolution of the LDGM-LDPC codes. Before that, we have one or two slides introducing what density evolution is. And essentially a iterative decoding technique using message passing. Density evolution is of course suboptimal compared to ML decoding because the error thresholds are lower than the ML thresholds, but the advantage of this technique is that it's computationally feasible over sparse graph codes. It's an iterative process where what you try to establish is that the error in the nth round, when you talk about error in the binary erasure channel, it's the erasure in the nth round is related to the erasure in the L-1 of the previous round. And then essentially you study how does the erasure change over the iterations. And what you're trying to find is you're trying to find the fixed points of the density evolution process, because that's where density evolution halts. And no more erasures can be resolved. And of course, there are stability conditions. We will talk about those. What's the significance of a stability condition? So as an example, let's look at an LDPC code, which the standard irregular LDPC code defined by lambda and rho. And this is in fact the equation for the fixed point. In fact, this is the density evolution equation. This is the erasures in the L-1 stage connected to the erasures in the next stage. So this is an iterative process. Initially, x of 0 is epsilon, which is the erasure probability of the binary erasure channel. Should be. So x naught is in fact the erasure probability on the channel. And this is some kind of an iterative map. As long as x of L is less than x of L minus 1, you're good, because erasures are reducing. And in fact, this slide is a little confusing. So let's look at, in fact, the equation. XL equals lambda of 1 minus rho, 1 minus epsilon, or 1 minus XL minus 1. In fact, we can see that the point x equals 0 is a fixed point for this equation.
If you see what lambda is?
Initially, he defined it as the degree distribution of the variable nodes.
Yes.
And the rho is
And
the
check. So now let's look at the equation. X equals epsilon lambda 1 minus rho 1 minus x.
For LDPC, LDGM, we have more of these distributions. We have the ones for H and for G.
All right, and what we'll do is we set x equals 0 on both sides. Well, let's start with setting x equals 0 to the right-hand side. We get delta times lambda of 1 minus rho of 1. Rho of 1 is 1. So you find that the right-hand side is 0. So the conclusion is that x equals 0 is a fixed point for this equation.
Where did delta come from?
Delta is the erasure probability of the binary erasure channel.
Okay, so what's that iteration?
Beg your pardon?
What is that? What is that iteration?
This is the equation for the. This is the equation for how the erasure evolves over a LDPC code.
You're missing he's asking you where is the delta in your equation.
Oh, where is the delta in the equation? That's a typo, it's missing.
Oh, thank you, sir. Okay. And if I'm not mistaken, that's very close to a classically chaotic map.
Yes. And in fact, that's what you do. When you have a system like that, and you want to study if a certain region is stable, you expand the Taylor series around that region. Okay? And this is the first order term, and this is the second order term. And you assume that XL minus 1 is very small, so you can neglect the second part. And essentially, the first coefficient governs whether this is stable or not. So that's the necessary and sufficient condition. As long as this coefficient is less than 1, this is familiar. As long as this is less than 1, there is always a xi, such that for all erasures in that range, the iterations will eventually land up with x equals 0, which means you've resolved all the errors. And this is stolen from Wolpanke's book, this picture, which is essentially an exit chart interpretation. This is the curve C of x, which is 1 minus rho 1 minus x. And this is mu inverse of x. Essentially, you can see that.
And now you're mixing epsilon is delta, right?
All right. Sorry about that. So here's a disclaimer. Give me a second. So this is a composition of mu and c. And as Professor said, we mix them up. All these are deltas. Sorry about that.
And no, I made a very bad error. It's a linear equation, period. So it's not chaotic at all. I thought for some reason I was thinking it was an x outside. So,
But the idea is that this equation is nonlinear.
So
This equation is nonlinear, but you take a linear approximation.
that's pretty standard.
Sure.
I thought it was something else.
No,
So
no,
it's not what I thought.
this
it
is
was.
all it is.
So I made an error.
you have to be careful when you say yes.
All right.
It's not chaotic in any way, shape, or form.
So to see a graphical interpretation for this, this stability condition, all you're saying is that the slope of this curve is higher than the slope of this curve at x equals 0. That's the necessary and sufficient condition for stability at x equals 0. So this is sort of an introduction of what happens in the LDPC world. Now let's look at our old friend, which is the code ensemble CHFP. Okay. So just to remind you, these are the bits x1, these are the bits x2 punctured independently with probability p. And essentially this is very similar to an LDPC code. So we essentially we define x1, y1, x2, y2, etc. the erasure probabilities in the nth round. These are the equations for the way the probability of erasure evolves. And these are the fixed point equations for x2 and x3. By the way, what are rho and lambda? So these are the generating functions from the edge and the node perspective. Okay. Now let's try to look at the stability of the fixed point x2 equals 0. Essentially, we do the same thing. We take the Taylor series. Of course, here it's a function of x2 and x3. So we take a partial derivative and we take the Taylor series, and you essentially get these two
I think
results.
what's missing is what's x2 and what's x3.
Oh,
You didn't sort of like remind them.
sure. So this is x2. Is the probability of an erasure going into the LDGM accumulate nodes. And x3 is the probability of erasure going into the LDPC check nodes. Okay. So actually, if you know either one of them, you know whether the system will converge to a no error system. That's pretty clear for me. If x2 is 0, in the LH state, and you know all the variables.
What about X3? Same thing, right?
You need it.
Yeah, but if you know only X3, it's also sufficient.
So here's the thing. These bits depend on these bits. And the reason is,
So if you know
X3, this, then you know that.
If you know X3, then you know all the LDPC variable, then you know all the X2s, and then you know that.
So either one of them is sufficient. And this is in fact the stability criteria for density evolution around the point x2 equals 0. And this is the equation, and it's quite complicated, much more complicated than the LDPC case, which is just this. So at this point we can speculate, because what does this equation tell us? One of our Banker students interpreted what this means, and what he says is this equation in some ways is bounding, or is essentially what it says is that if this condition is true, then there are no cycles in the original LDPC code where the variable nodes have a degree 2. Okay. So somehow he shows that if such kind of subgraph is not present, then in fact decoding will complete. Okay. Decoding will go to completion. That's the idea. And
We'll start there.
no, it will conclude. You'll fix all the erasures. And the question is, why is it a bad idea to have an LDPC subcode where all the variable nodes have degree 2? Well, the idea is this: it forms a support set of the code line. And if those bits get clobbered, then there's no way you can recover. So that's the intuition. Okay? The idea is it's upper bounding the probability of finding a variable node of degree 2, because that's the troublesome part. Our equations upper bound the probability of finding LDGM variable nodes and LDPC variable nodes of degree 1. So what is the graphical interpretation of that? I don't know. It's possible that you couldn't have similar results and you can show some cycles. It's all speculation. So this brings us to the final part of the talk. Now what we do is we apply regular LDGM-LDPC codes for secrecy coding. So the first slide is on why we need physical layer secrecy. And we know the applications of wireless networking and the essential weakness that wireless signals are broadcast. And if we don't want any cryptographic infrastructure, the question is, can we provide secrecy? And the answer is yes. If you were to exploit the statistical properties of noise in the eavesdropper's channel, then it's possible. And that's what physical layer secrecy is all about.
So what's eavesdropper?
Oh, we'll define that. We'll just come to it. So we've seen the nesting properties of LDGM-LDPC codes. That's what we started with. And I'll just look at some of the applications of binning. And binning is defined as partitioning a code into disjoint bins, such that the bins have a certain property that the elements of a bin are as far apart in Hamming space as possible. Okay. If indeed we're talking about binary coding, for example. And the applications are in secrecy, in source coding with side information, channel coding with side information, coding for memory with defective sets. I don't even know what some of these things are. Digital watermarking. So
It's a long time ago for me. I don't remember that long ago.
It's only a few
It says the page is still there.
Please describe.
Now, the essential idea is that you have a code C0, which is known as the finite code, and you partition it using a code C1, which is a subcode of C0 and its cossets. So this guy is a subcode of C0, and then you take this code and then you compute its cossets, and you get, in fact, all the cossets together constitute the partition of the fine code C0 of n. This picture is a little misleading though, because somehow this picture seems to tell us that, for example, if you look at this bin, this code word and this code word are very close. In fact, the opposite is true. In the Hamming world, they are as far apart as possible. So, this is just conceptual. Yes? Oh, actually, you're right. The nesting property that I discussed in the beginning of this talk applies to irregular codes as well. Okay? So the reason I use regular LDGM-LDPC codes is because I know their spectrum. Okay? To prove certain error properties, to prove noise thresholds, I will need the spectrum. Yes, the weight spectrum of the code. Okay? And I don't know how to find the weight spectrum of an irregular LDGM-LDPC code. In fact, I don't even know how to find the weight spectrum of an irregular LDPC code. So, I use the regular codes. The third point says that regular LDGM-LDPC codes can be used for binning. We saw in the beginning of the talk. Now we come to the Wiretap channel model, which was proposed by Raina. And the model consists of a transmitter, a receiver, and an eavesdropper. And Raina and Zyro considered a special case where the main channel is in fact noiseless. It's known as type 2 channel. So this is the Wiretap channel model. This is the transmitter. He wants to transmit a message which is received by the legitimate receiver and the eavesdropper after it goes through two different channels. The transmitter chooses the messages uniformly from a certain message set, which is publicly known. And it essentially encodes the message, random message W, into some code word XN. And due to the channel noise in the respective channels, you get YN and ZN respectively upon transmission of X of N. And the goal, so over here, we have a box. Actually, there should be an encoder, but I haven't shown it. The box encodes the messages. And the code we use should have two properties. It should be extremely reliable, which means that regardless of how bad the conditions on the main channel are, the coding which is performed here, the coding which essentially maps W to X of N, is strong enough such that the legitimate receiver is able to recover X of N, and from that he can map back to W. That's the first requirement, which is known as the reliability requirement. And then is the secrecy requirement, is that the coding scheme should be such that it also confuses the eavesdropper completely. So when the eavesdropper receives Z of N, he has no clue how to reconstruct or conclude what W was.
I've forgotten how equivocation is defined.
Oh, it's right here. The equivocation is essentially the uncertainty of the number of bits, the fractional number of bits, which the eavesdropper is ignorant of, given the fact that it has Zn. And essentially, the equivocation must be at least R of E, where R of E is your chosen equivocation rate. If R equals RE, this condition is called perfect secrecy, which means that the eavesdropper has no idea what's going on. And the eavesdropper is not able to infer even one bit of information of the message. And for a given wiretap channel, if the main channel is less noisy than the eavesdropper's channel, then the secrecy capacity is defined by this expression, where I is the mutual entropy. But I try to read the...
It's not the same as the mutual information between the sender and the eavesdropper is 0.
Big part. Eavesdropper 0.
The mutual information between the channel capacity, I mean, that's what you're saying, there's a rate between the user and the the sender and the desired receiver.
Mm-hmm.
The eavesdropper should see no mutual information. It should be, so that's equivalent. And I guess I just have to write out the identities to see that, right? Is it correct to say that the mutual? Is it correct to say that the mutual information is 0 between sender and eavesdropper?
No. Yeah. What's IXC? What's that?
That's the mutual information between X and Z.
What's X and Z?
The transmitted code word and the received code word.
Is that 0?
C is the eavesdropper reception?
Yes.
Yeah.
I'm not sure.
What's IX1?
That's the mutual information between the transmitter and the legitimate receiver.
And that's bigger or less than, or well, how's that related to RE?
It's not.
Okay.
So what is related to RE is this.
Oh, I'm sorry. How about then R is what? Transmitted rate, right?
Mm-hmm. So this is related to R.
So that's the, that expression there is the capacity of the eavesdropper's channel, right? Secrecy capacity? No, sorry, that's the
This is the
difference.
secrecy capacity. So this is the highest rate at which you can transmit information and keep E completely ignored, or the eavesdropper completely ignored. That's what it is.
And he's asking, why doesn't that just mean that IXZ equals 0?
Which is a perfectly legitimate, if stupid question. I'm just asking you to dispel me my ignorance.
Well, if IXZ is 0, which means
If you look at the diagram, maybe it's going to help you.
if IXZ is 0, which means there is no mutual information between X and Z, then in fact the rate of the main channel is the secrecy capacity. That's what it is.
Okay, so let's do a simple example. Let's suppose that they're both AWGN. What happens then? There's no fading, just
Sure, if they're both
just an R for each channel.
if they're both binary input AWGM, then in fact they're maximized by the same P of X, which is the uniform prior. And then in fact the secrecy capacity would just be,
I'm sorry, you really confused me there.
maybe I'm confused.
A uniform prior?
The
Well,
uniform prior is
he's using binary input. He's considering so we can talk about binary input, that's fine.
sure. And essentially the secrecy capacity is just the difference of the capacities of the main and the eavesdropper's channel.
So is I at XC 0?
Oh, it cannot be.
It can't be 0, right? So there is something that's kind of zero, right? What is zero? There is a mutual information floating around here that's arbitrarily small that you care about.
But the equivocation is large. If the equivocation is in fact n, then I of x z is 0.
No.
No?
You should look at the graph, that's gonna help you figure it out. The
I of x z is
block
this number
diagram.
here. There's no doubt about that.
Mhm.
It is.
Look at the block diagram. So now think about it. So the mutual information between x and z is the eavesdropper channel, right? What do you want to make to be zero? Which mutual information?
Are you saying which mutual information should be 0?
Or
Ideally?
very close to zero.
Sure. So ideally, this mutual information should be high, and this mutual information should be
Well,
absolute.
no, we agreed it's going to be this number over here, and you can't make it smaller. The channel's given to you, and you're using equal probable binary input. So I of xz, it's, you know, it is whatever it is you get with a binary input made of BGN. So somewhere in this diagram are some symbols that there's a mutual information there that you want to be really small. Which one?
That would be this one.
I don't think it's.
No, because that one is given.
Assume it's given. Come back to the block diagram. Go back to the block diagram.
Okay.
So assume main channel is given and eavesdropper channel is given. What do you have control over?
The coding scheme.
Okay, so how can you, what do you want to make small using the coding scheme? Which mutual information?
And what are you hiding from E?
What are you hiding?
What are you going to prevent E from knowing?
X of n.
No, she might know, she might learn a lot about X of n.
Or W.
Here we go. So what mutual information is small? Like one that has W in it.
Right, I'm sorry. Okay.
Yeah.
So it should be I of W and Z of n.
Right.
Sorry.
Nice.
Yeah, yeah.
Thank you. Less noisy means this quantity is essentially greater than this quantity.
That's more capable.
You know, I'm sorry, that just occurred to me, I've got even another question, really, I'm just gonna beat you up. Yes, you did. Go back. So we just established that we don't wanna know what the message is. The transmitter or your coder, if I give you a W, so forget about any eavesdropping. If I give you a message, does a unique code word XN pop out?
Yes.
Unique.
And
What's the unique?
So you're saying if you have a W, then you have a unique X of n. Is that
It's a one-to-one mapping.
Sure, it is. That's how code is, right?
So not all.
So let's just play with it. So if it's a one-to-one mapping, right? It's invertible, right? So I think you just said that if you're trying to drive mutual information between W and Z sub n to 0, then I think you just said you automatically drove the mutual information between X sub n and Z to 0. Would you show that that's not necessarily true? I know I'm a little jerky.
So maybe quick timeout. What was Weiner's most basic code construction? Mapping W to XN.
Was it one-to-one?
Yeah, that's where I was going.
So Weiner's construction was essentially using a bin. So you map a message to in fact a bin, and then it's no longer one-to-one because
So how do you choose the code that you take out of the bin?
uniformly.
All right, so you add some uncertainty.
Yes.
So there's essentially two messages going on here. There's
Right.
the uncertainty associated with which message you pick, and then this message itself. Okay.
Thank you.
Okay.
I told him last time not to be nervous.
Oh, yeah, he didn't know I was coming. Take a deep breath. I'm not. This is not done in rank or anything.
Sure, I sat through a class and I took your exams. I lived through that, I lived through this.
So he froze when you came in. That's what it was?
But thanks, that was clear.
So, after a deep breath, the type 2 binary symmetric Wiretap channel is essentially this. You have a noiseless pin channel and an eavesdropper channel, which is a binary symmetric channel. With a crossover probability of P. And the secrecy capacity of this channel is H2 of P, and that we can see from this expression. Because this channel is essentially noiseless, this is 1 minus HP, so you have a secrecy capacity of H of P. Let's look at some previous works on secrecy coding or the type 2 binary symmetric Wiretap channel. And by the way, this is the secrecy capacity curve H of P. As we saw, this is the secrecy rate and this is the crossover probability. And Fungaraj use error detection codes to achieve secrecy rates of log of 1 minus P, which is this curve. Rohin used a combination of 2 coding techniques to essentially achieve a secrecy rate of 2p, which is this straight line.
Over the same channel?
Over the same type 2 binary symmetric Wiretap channel. And the question is like, how do you jump from here to here?
So why did you say this is over a degraded BE state?
We'll see what that means. We will come back to that. So this is a slide about Weiner's random meaning scheme is what we were talking about, that essentially you have this whole code book. These little squares are code words. And essentially what you do is you partition the fine code into bins, and then you randomly choose, uniformly choose a code word when you have to transmit a certain message. So message I corresponds to bin I, and then you uniformly choose a code word from bin I and you transmit. So this slide is stolen from Jajun, and essentially shows us why secrecy coding works. And assume that this is the set of, this is in fact, these circles are the elements of fine code. And this is bin 1, this is bin 2, and the red is bin 3, suppose. Okay, suppose you transmit this message, and suppose you transmit this, in fact, and you receive this. So you transmit this, and the legitimate receiver obtains this. Okay. The essential idea is that suppose the legitimate receiver uses some kind of minimum distance decoding or bounded distance decoding. He can resolve a unique code word, okay? Because that's the only code word in this Hamming sphere. On the other hand, the eavesdropper sees 3 code words in its Hamming sphere, and not only that, all the 3 code words are from different bins. So that's why the scheme works.
What was the assumption on the adversary? And why does the adversary see 3 and not?
Because it's assumed that it's more noisy than. That's why the radius is larger.
But it's really, the assumption's really Like, it's not just that the adversary sees a couple, right? Few is possible, acceptable things as code word. He actually, I mean, there's a stronger statement to be made. I was hoping you'd finish my thought. I mean, like, if he sees only 3, right, he has a sort of a 1/3 chance of guessing all of the bits correctly.
Oh, sure. So in fact,
So-
he should see one element from every bin that you.
That passes, that looks like a code word, that could match what he received, right?
Then he's completely screwed because he doesn't know which is which.
Well, here, there's only 3 bins.
Oh.
He sees all the colors.
Ah, 3 bins, okay. Yeah. Right, okay, thank you for trying. Some of those pictures aren't usually with just 3 bins.
Yeah, it's like
the
3
bins are.
3 is an odd number, you know?
Yeah.
You never get 3, bins. You always get power of 2.
So of course the binary scheme is for practical coding you would use binning. So what you do is you consider a coarse code C1 which bins fine code C0, and that's the basis for partitioning. And essentially what you do is that you use the cosets of C1. That's how you transmit your messages. This slide talks about previous works. This is the work by Thangaraj, where he used error detection codes and achieved a secrecy rate of log 2 over minus p. Okay. And what Rohan did was he modeled the BISOM channel, which is the eavesdropper's channel, is essentially a degraded version of a binary erasure channel. That's what. So this BISOM channel is a degraded version of a binary erasure channel.
I guess what's important, what maybe you missed is, at some point you said that in the bin you want codes to be as far as possible. But to achieve perfect secrecy, there's even a stronger condition. What is the condition of the binning code?
Right. So there's a very strong sufficient condition which says that if the binning code C1 achieves capacity of the eavesdropper's channel, then perfect secrecy is possible. So it's a very strong statement in the sense that it's a sufficient condition. So if C1 of n, which is your binning code, achieves capacity of the eavesdropper channel, then there is this theorem by Thangaraj where they show that perfect secrecy is possible. Of course, that does not rule out other codes which don't achieve capacity from achieving perfect secrecy. That's why it's a very strong statement. What Rohan did was he followed 2 strategies. The first strategy was to partition all the n-length vectors 0, 1, n using a LDPC code, and what he would have is essentially a coding system where the transmission rate was always higher than the equivocation rate. Okay. So that's strategy 1. And the other strategy is a coset coding scheme where he uses a dual of a good code to bin 0, 1, n. And it shows that in fact, if you know z prime, then you know nothing about w, so you get perfect secrecy. Then he uses a time-sharing scheme. Up to a certain point in this curve, I'm not sure. This is the equivocation rate. This is the transmission rate. I'm not sure where that point is.
Where you can see the blue curve, the parts.
Right there. I think this is the point. Rohan uses the degraded Wiretap channel principle. And along this region, you can see that the equivocation rate is equal to the transmission rate. And then he starts using the other scheme, that is to bin 0, 1, n. And there you see that there's a departure there's a gap between the equivocation rate and the transmission rate. So there's a gap.
Where is the secrecy capacity in that region? Does he achieve secrecy?
No. So the secrecy capacity region would be,
There's secrecy capacity is not a region, it's a point.
this is the point.
Okay, does he achieve it?
No, because there's a gap here.
That gap was just the.
No.
No, it's a gap.
Oh, that's a good.
Oh, by the way, it's, yeah, there's. So what we propose to do is, we take the course code to be the set of all n-length vectors, and we do that because we don't have to defeat any noise in the main channel, because there is no noise in the main channel. The main channel is noiseless. So C0 of n is in fact all the set of n-length code words, and C1m is a capacity achieving code for the eavesdropper. Okay. We partition C0n using the cosets of C1, and to transmit a certain message, we essentially choose the ith coset and transmit a code word at random. And essentially we prove that this coding scheme achieves secrecy capacity of the type 2 binary-symmetric Wiretap channel. Essentially what we show is the equivocation is greater than h2p minus this quantity. Okay. Let's look at the uncertainty of x given y, given w and z. If we knew w, if we knew which coset the message comes from, and if we know that, given that we have a capacity achieving code, the coset shares the minimum distance property of the original code C1, and therefore, given the sequence Z of n, we should be able to derive, we should be able to conclude what x of n was. And that's essentially this. And now we use regular LDGM-LDPC codes as fine codes, and we use the same principle. The only thing is C1n is carefully chosen regular LDGM-LDPC code, which is capacity achieving with finite increase. Now we look at some numerical examples of this idea. So the first thing we have to do is how do we show that a regular LDGM-LDPC code in fact comes close to the capacity? So for that we use typical pairs decoding. And we derive the noise thresholds for the code. What we do is we use a theorem by Hui Jin. And essentially what he says is that if RD, which is the spectrum of the code, is less than a certain function given here, for all values of D, then the typical pairs decoder will decode the code with 0 error probability. And that's one of the things. We ran into this difficulty because we needed to know the spectrum of the regular LDGM-LDPC codes. That's another thing we proved in this paper. We derived the spectrum. It's in the appendix. So now we calculate the thresholds for certain LDGM-LDPC codes given here. These are the degrees. This is the rate which is achievable. This is the Shannon threshold, and this is the actual threshold obtained by simulation.
You mean by numerical evaluation?
Yes, that's what it is. Yes. So what we mean by numerical evaluation is that we know the spectrum and we know this function, we start increasing the value of P and see how close we can get such that this condition is true. And in fact, what we show is that the codes which we discussed in the previous slide fall on the secrecy capacity code. And there's a good reason why we don't have any numerical evaluation in this region, because to get anything there, the degrees become really large.
So,
It's no longer low density. I imagine the LDPC code is
Somehow you're in the blue curve.
no, this is the secrecy capacity code.
Yeah.
These points are the secrecy rates achieved by specific.
Ah, I see, yeah, yeah. And the blue curve is Romane's curve.
Blue is the Rohan's curve, and the green one is
Is
the
the
curve.
triangle.
so you see the thing that is key, I think, here with LDPC, LDGM is these numbers, 2, 3, 5, you know, that's the degree of the lambdas, right? And they're
Yes.
very low. You know,
Right.
if you use like LDPC codes, these numbers would be much larger if you want to be at the capacity.
Actually,
Because they're not functions.
They're functions, but they have degrees, right? How many, and these degrees is like how many, what's the percentage of the edges of certain number, right? And you know, so this is like, in this case, if it's a regular code, then all edges are degree 2.
Okay.
So this is regular, right?
in fact, one
But
thing.
very sparse.
So yeah,
Very
only
sparse.
two, you know, it's very sparse. It's only 2 connections. It's only 2 zeros in a row of an H matrix,
Right.
and three ones in a G matrix, right? Or 4 or 6.
So at this point, you can ask yourself a question like, you know, if I was not using the regular LDGM-LDPC construction, but just a regular LDPC construction, that was the question in ITW, like, what happens? And if you see which things work, what it shows is that regular LDPC codes, their thresholds fall far below capacity. So clearly the upper LDGM there is doing some kind of concentration. Essentially, if you evaluate the spectrum of these codes, and that's what we did in this paper. So if this is, for example, the LDPC code spectrum, this is the weight. This is the spectrum. This is 0 and 1. What does the LDGM layer do when it's concatenated to the LDPC code? And essentially what it does is this is the LDGM LDPC. So what's going on here? Essentially what you're doing is you're ensuring that you have fewer code words with lower weights. Okay. So the upper LDGM layer is acting like some kind of a concentrator. It's taking code words from the low weight regions and putting them here. Essentially what's doing, in some sense, it's enhancing the distance property of the original code. Okay, and that's the reason the thresholds are high.
Let's do the question once gamma again.
Oh, that's R. I'm sorry, it's not gamma. This is the spectrum. The spectrum of the code.
How do you define a spectrum?
Okay.
Like a log of.
So, like A of n delta is a weight enumerator. That is to say, if delta lies between 0 and 1, what are the number of code words in the code with weight and delta? Now, assume you know the weight enumerator, the spectrum is just limit n tends to infinity log of A n delta divided by n. So essentially, the spectrum, you're saying that the weight enumerator is some kind of exponential function of n And if you want to look at the exponent, that is what the spectrum is.
Right, and the weight is just against two
The
different.
weight is the Hamming weight.
Right, so it's an integer.
Yes. So strictly speaking, delta is not continuous. It increases in small jumps.
But you let n go to infinity, so these jumps are very small.
Sure.
These are all asymptotic.
Yeah, I was just looking at the thing that caught my interest was the negativity.
Yes. So what does the negative region mean? So when the spectrum is negative, it essentially means that there are only a polynomial number of code words in that region. Yes, that's what it means. But essentially, the code words should be exponential number, but in those regions, there are only a polynomial number of code words. Okay, so that's what the LDGM layer is doing. Essentially, is it's concentrating code words from these regions and putting them here. And that's the reason they have better distance properties. And the question was, why did Michelle was asking the question of why regular? Well, you see, these are the kind of things you can do with regular codes which you cannot with irregular codes. Because if you have an irregular LDPC code, even finding its spectrum is not easy. But for a regular code, you can do these things and visualize them. Okay. Now let's look at the rate equivocation region for a type 2 symmetric binary-symmetric Wiretap channel with a crossover probability 0.214. I just chose a crossover probability at random because I had a code for it. Okay, and essentially this was the equivocation rate versus the transmission rate for the Hink scheme. And using nested LDGM-LDPC codes, you can see that it goes all the way up to the secrecy capacity point. And this is the appendix. This is the, just in case you want to know what the spectrum looks like. This is the weight enumerator we derived. This is, of course, an upper bound. So to conclude, we partition the set of vectors 0 and n using a capacity achieving code, and we achieve the secrecy capacity of a type 2 binary symmetric Wiretap channel. Thank you.